Good morning. I'd like to welcome everybody to the 2019 Bow Award presentation ceremony. The award is in memory of Professor Robert Bow, University of Southern California, from 1969 to 2008, and president of the ACA in 2006. He was a much beloved teacher and mentor, and Professor Bow made numerous contributions to development of techniques of single crystal neutron diffraction and its applications to chemical and macromolecular crystallography. The award was established in 2010 and is presented triennially, and the award recognizes exceptional research in neutron diffraction. The previous award winners are Tom Ketzel in 2013 and Benno Schoenborn in 2016. The 2019 winner is Bryan Chakoumakos. Bryan is a distinguished research scientist at the Neutron Scattering Division at Oak Ridge National Laboratory. He conducts research on the properties of novel and technologically important materials. He employs crystallography and X-ray and neutron diffraction and publishes in physics, material science, and mineralogy journals. Bryan received his PhD in geological sciences from Virginia Tech in 1984 with Jerry Gibbs. Immediately after finishing a PhD, he became a postdoc at the University of New Mexico and worked with Rod Ewing. And why is this not scrolling? There we go. Here we go. At Oak Ridge, he has been an instrument scientist for the powder diffractometer and the four-circle diffractometer at the high-flux isotope reactor, and he has served as group leader for 11 years for diffraction groups involving instruments at the HFIR and the spallation neutron source. Bryan is a fellow of the Mineralogical Society of America, the American Crystallographic Association, and the American Association for the Advancement of Science. He served as associate editor and letters editor for the American Mineralogist. He currently serves as secretary of the Mineralogical Society of America, and other activities that he has include serving on the board of the scientific directors for the National School for Neutron and X-ray Scattering, which is now in its 20th year. For the past 10 years, he has also chaired the Neutron Scattering and Powder Diffraction Special Interest Groups of the ACA, and he is a member of the Research Committee for the Japan Atomic Energy Agency, U.S. Department of Energy Cooperative Program for Neutron Scattering. He's also served on the Intense Neutron Pulsed Source Program Advisory Committee. I have a quote from one of his colleagues showing how much he's appreciated. Bryan is a very nice mentor for the group, and I have supervised some young early career scientists to some very successful careers. So with that, we'll do the award presentation, and Bryan will give his lecture.
Okay, thank you, Joe, for those kind and generous words. It's a little scary when you hear your career summarized like that. It's a pleasure to be here, and I'm very honored to receive this award, and also still very surprised and humbled by it. In my lecture today, I'm going to give a few historical snippets, a reminder why neutrons are a powerful probe, a pedagogical example of a battery material from a reactor-based experiment. I'll show you some insights that I've used to look at atomic displacement parameters as a function of temperature, an example of magnetic diffuse scattering from a spallation source instrument, and lastly, an update on the single crystal diffraction suite at Oak Ridge. So the history of neutron sources for neutron scattering at Oak Ridge spans 76 years, and it was born from the Manhattan Project. With the construction of the graphite reactor, also known as the X10 pile, which was ultimately a 4 megawatt reactor. It was built in 9 months and went critical on November 4th, 1943. Neutron scattering began with the graphite reactor, progressed to the Oak Ridge Research Reactor, which you don't hear as much about. I'll mention a few things today that were of significance. That was a 20 megawatt reactor. Then to the high flux isotope reactor, which began operating in the mid-60s at 100 megawatts, where later a cold source and guide hall were built. And then finally, we now have the spallation neutron source. Anyone that's worked at ORNL becomes interested in the history, particularly of neutron sciences, since Oak Ridge is considered the birthplace for the discipline. The historical notes I'm going to show today in the beginning of my talk are just a few examples of the crystallographic contributions and connections. Ernie Wolin came to Oak Ridge in 1944, and he had studied with Arthur Compton at the University of Chicago. A few months after the graphite reactor began operating, he wrote this letter, and the letter reads, "I would like to attempt to measure the diffraction of neutrons by single crystals. I have brought some equipment with me from Chicago, and Dr. Borst has shown me an opening in the pile." The pile was the graphite reactor, "at which this work could be done. I would appreciate obtaining approval to go ahead with this experiment." Oops. So Tom Mason gives an account of this early development and comments that this was perhaps the very first neutron beam time proposal, and certainly could be considered marking the beginning of the discipline. In the summer of 1944, Walter Zinn had observed neutron Bragg peaks from calcite at the CP3 reactor, which is at Argonne. And neutron diffraction had already been demonstrated earlier in 1936 using radium-beryllium neutron sources. This was done by Mitchell and Powers at Columbia University. But weeks after Zinn's experiments, Wolin showed the same thing for gypsum and halite. And here on the left are Bragg peaks that he recorded using the graphite reactor. Clifford Shull joined Ernie Wolin at Oak Ridge in 1946, and the pair began to explore the field in earnest. And over a 9-year period, they built the foundations of elastic neutron scattering. On the right is the first neutron Lowry diffraction pattern recorded for, in this case, sodium chloride. It's about a 3.5 millimeter crystal. It's a 10-hour exposure using the white beam from the graphite reactor. And the detector was simply strips of indium foil placed against some photographic film. And if you look closely, you can even see the shadows of the Scotch tape that was used to hold the indium strips together. Shull and Wolin were prolific during the 1950s, publishing a number of seminal works. This one in particular experimentally proved the proposal by Néel of antiferromagnetism. The magnetic cell is bigger than the nuclear cell, and you can see the magnetic Bragg peaks of the larger cell appearing at low temperature here in the top and absent at high temperature. Another seminal work was elucidation of the magnetic structures of what later became the archetype materials for the colossal magneto-resistant manganites, the lanthanum calcium manganites. To do this work, Wolin and Kohler actually built a cryomagnet, which is shown in the drawing on the left. And they enumerated all the possible magnetic structures for this family of compounds. And this turns out to be perhaps the most cited paper of all the neutron program at Oak Ridge. Shull left Oak Ridge in 1955 to go to MIT, where a university research reactor was being built. Students of Shull, shown here, Steve Spooner, Herb Mook, and Ralph Moon, all later came to Oak Ridge and had distinguished careers. The gentleman on the right here is Mike Wilkinson. He was a longtime director of the Solid State Division, which managed the neutron scattering programs at the ORR and the HIFER for just prior to my arrival at Oak Ridge in the late 80s. Prior to receiving the Nobel Prize in Physics, which was shared with Bertram Brockhaus, Shull was awarded the Grigory Amanoff Prize, an international prize awarded since 1979 by the Royal Swedish Academy of Sciences in the field of crystallography, and considered the highest honor in our field. Note that Ernie Wolin would have surely shared in the Nobel Prize had he not passed away years earlier, in 1984. Here's a model of the ORR, the Oak Ridge Research Reactor. It achieved full power in May 29, 1958. It was a multi-purpose reactor to make radioisotopes and to do nuclear engineering and neutron scattering experiments. It was a pool-type reactor, and it looks a lot like maybe a tugboat, except that the water's on the inside of the boat rather than on the outside. This, in effect, was the prototype for the HIFER. Here's some recognizable distinguished visitors at the ORR. This was prior to JFK becoming president. He was still senator at the time. Jackie Kennedy has her hands in a radiation monitor, one of the many radiation detection devices that were developed at ORNL. There's several significant events occurred at the ORR. One is in 1962, Mike Wilkinson and Harold Smith built the first triple axis spectrometer in the US. And this was based on the instrument design at Chalk River that Bertram Brockhaus had built. The first SANS in the United States was also built at the ORR, and this was the prototype for the dedicated instrument that was later at the HIFER. And the first automated neutron three-circle single crystal neutron diffractometer was built here. And it looks like this, where it has a chi-circle, a phi axis, and a 2 theta arm that's synchronized by levers so that you maintain a bisecting angle or theta 2 theta relationship. The data collection was controlled by a computer program that prepares a paper control tape, and it printed out the listing of the angles to be set. And it was using this Oracle computer, which was a large, monstrous first mainframe computer at Oak Ridge. And you can see more about the details of the history of the computer development at Oak Ridge in Bill Busing's memoir in the ACA archive. Of course, seminal structures, there were a few seminal structure studies done with this instrument, including the precise structure of sucrose. At this same time, Henry Levy led a crystallography group in the chemistry division. And Henry served as an officer in the ACA, first as secretary in 61 through 63, and then president in 65. He worked with Bill Busing, who also was an ACA president in 71 and received the Berger Award in 1985. These are two of the early automated, or two pictures of the automated X-ray system that was built using the PDP-5, which was really kind of the first mini computer. And in that left-hand photograph is a picture of Sharon King, who was one of the early computer scientists at that time and worked throughout her career with the neutron scattering program at the ORR and the HIFER. Now, during this period, the crystallography group, headed by Levy, produced much of the mathematical recipes and programs that would become the basis of modern-day computer-based crystallography. There's more about this in Busing's memoir, but certainly things like the analytical absorption corrections, least squares refinement, bond length corrections for thermal motion, plotting atomic displacement parameters, and the all-important UV orientation matrix recipe were all developed first on large mainframe and then rewrote for smaller computers that were being developed at that time. Here's an early photo of Carroll debuting the ORTEP program, which had huge popularity and still does. Carroll served as president of the ACA in 1977 and received the Berger Award in 1997. Moving to the high flux isotope reactor, it is now approaching its 483rd fuel cycle. So over the life of the reactor, it's averaged 9 fuel cycles per year. In recent years, we only run 6 to 7 fuel cycles annually. There's a great many noteworthy scattering studies done related to magnetic structures and superconductors and so forth. Particularly all the rare earth element magnetic structures were enumerated at the HIFER. A particular noted structural study was on the Keggins pentahydrate. But one of the papers I'd like to showcase here is the polarization analysis of thermal neutron scattering that Ralph Moon, Tormod Riste, and Wally Kohler developed. This was using a triple axis spectrometer in an elastic mode. And this technique permits the accurate separation of magnetic scattering from nuclear scattering. And it's widely used by all around the world. What makes neutrons excel for structural and dynamical studies is that the wavelengths and energies match the length scales and energies of those fundamental of matter. Neutral particles, magnetic moment, they see the nuclei, so have isotope sensitivity, and they have spin. We can polarize the neutrons. Contrast the X-ray scattering factor fall off with scattering angle versus none for neutron scattering here for probably a Martian mineral. Isotope sensitivity for neutrons allows for contrast variation, particularly popular for hydrogen deuterium, one of the signature applications for neutron scattering, primarily in soft matter studies. Different isotopes can give dramatically different patterns and fidelity to distinguish site occupancies, particularly for light elements and often for neighboring atoms in the periodic chart. Now to a pedagogical example. Here, consider the battery material, lithium iron phosphate, which I lifted out of a review by Goodenough and Kim on why this is an important battery material. Despite that battery materials are typically polycrystalline or nanocrystalline, single crystal studies can offer insight into their intrinsic properties. I often look for the mineralogical realm to find big crystals. You can find neutron-sized crystals of the whole solid solution of lithium iron phosphate, the pure lithium manganese phosphate. They have the mineral names triflite and lithiophyllite. In granitic pegmatites throughout the world, sizable crystals can be found where the initial magma composition determines iron-manganese ratio of the natural crystals. We have an ongoing study of samples we have personally collected and acquired through research collections and purchased as exotic gems. So of course, they're beautiful crystals, but you don't know the composition. Triflite lithiophyllite has the olivine structure type. The iron manganese is randomly distributed on the M2 site, and lithium is on this other octahedral site, forming octahedral chains. Given the marked difference in the scattering lengths between iron and manganese, we have great fidelity to refine the iron-manganese composition. And since manganese also has a negative scattering length, a null scattering composition necessarily occurs along the solid solution at 0.283 iron. At that composition, the M2 site does not contribute to the elastic scattering. Lithium has a negative scattering length as well, so it'll show up negative in density maps. The refined lithium atomic displacement parameters are quite anisotropic. And moreover, when we refine the lithium occupation, it comes out slightly reduced for all the samples we've examined. So then you can easily see that you have a diffusion path for lithium along the octahedral chain. If you look at the temperature dependence of the eigenvalues of the lithium ADPs, they clearly show that the 0 point values likely have some positional disorder associated with at least two of the directions, since they don't have a common intercept. Triflite lithiophyllite also manifests antiferromagnetism at low temperatures, 52 Kelvin for iron end member and 34 Kelvin for the manganese end member. And the manganese end member here has the moments aligned along the A-axis, whereas for the iron end member, the moments are aligned along the B-axis. The symmetry analysis that is used to aid magnetic structure analysis has been around for many tens of years. You can see some of the original papers by Berthaud in the mid-1960s. However, it's only in recent years that it has become so user-friendly. Here, I've just shown from the maximal subgroups of the gray group PNMA1', which is the supergroup for this triflite lithiophyllite structure type. And so we have these 8 possible magnetic structures. Using the Bilbao crystallographic server, you can easily display the allowed possible magnetic structures where the propagation vector is 0, 0, 0, so the magnetic cell and the nuclear cell are the same size. And you can see the moment orientations for the 4 magnetic M2 sites and the allowed moment components. In this case, MX and MZ are allowed. So if you look at the observed magnetic space groups that correspond to the ordered structures for triflite and lithiophyllite, these two occur. A little bit of iron stabilizes the moments in this direction with just an My component, and then the manganese end member has both an MX and MZ component, but realizes only an MX component. So the magnetic phase diagram for this solid solution has two phases. So let's continue and look a little bit more at the temperature dependence of atomic displacement parameters, which is kind of dear to my heart. Here's the canonical form of the atomic displacement parameter temperature dependence in a Debye approximation. Things to note is that at high temperature it's linear, and at low temperatures it's not extrapolate to 0 temperature, but has a 0 point vibration, which is inversely proportional to the atomic mass. So, lighter elements will have larger displacement, 0 point displacements. So the temperature dependence of the ADPs can reveal information about positional disorder and other anomalous behaviors such as aniharmicity at low temperature. We've used these simple notions to look at thermoelectric materials to gain insight in how one can tailor their lattice thermal conductivity, which is important for optimizing thermoelectric efficiency. Here, the clathrate-type thermoelectric materials such as the filled scuderites and the structure type 1 clathrate show anomalous temperature dependence of the displacement parameters of the atoms that are in the large cage. So you can see here the lanthanum, which is the heaviest element in this structure, which would, if all was not anomalous, would be down here, has a very large displacement and a large intercept. Same for the strontium-2 in this large cage. These are 2 sets of data, both single crystalline powder. These were all collected at the HIFER. Even if you use a split site model for the strontium-2, which shifts the curves down to here, they're still anomalously large. So we think of the caged atom as rattling in the cage, which is kind of an exaggeration. So the temperature dependence and the 0 point values for a series of these clathrate structures where you have europium, strontium, and barium in a large cage do not follow the expected behavior based on mass. In fact, what it seems to follow is the relative size of that atom. So barium is bigger than strontium, bigger than europium. So the intercept here corresponds to a positional disorder or a split site. And also they're loosely bound, so they have very large amplitudes of displacement. And we've been able to correlate these with the lattice thermal conductivity, particularly glass-like behavior for the europium and strontium. You can see the positional disorder in the large cage of these clathrate compounds in the Fourier maps or maximum entry maps. The split site models for strontium and europium actually improve the structural refinements. So when you consider the crystallography of clathrate-type thermoelectric materials, there are 3 points. The anomalous ADPs, okay, their magnitude, possible anharmicity, the positional disorder, which you can see in density maps, and also the temperature dependence of the ADPs. But a third thing is also important is that the framework metal atom distribution needs to be determined. This can be dependent on the thermal history, how for instance, gallium and germanium partition on the 3 different sites in the clathrate structure. So all of these then relate to the thermal conductivity and electronic behavior. We have developed, with Bryan Sales, we developed some recipes to compute lattice thermal conductivity and other thermodynamic properties based on the Debye model for the framework atom displacements and using Einstein models for the caged atoms, which became very popular. Let's look at another mineralogical example where fluorine substitutes for hydroxyl in this lithium aluminum phosphate, amblygonite and monobrazite. And what happens is it causes a positional disorder of the lithium site. So, you know, this is the crystal structure. Again, it occurs as large crystals in granitic pegmatites covering the whole solid solution range. Here shown in the red highlighted curves are the atomic displacement parameters as a function of temperature, where with increasing fluorine content from 0.04 to 0.77, you can see the 0 point displacement shifts up. So even these have the similar slopes. So what we're showing here is that the lithium 0 point displacement increases with fluorine content. And so the way we understand this case is that in the one end member for monobrazite, you have the hydrogen bond forming to O4. Of course, the bond lengths shift quite a lot, and the lithium O4 strengthens as the hydrogen bond to O4 is removed, and at the same time weakens the lithium O3 bond. And then you end up with positional disorder associated with that site. Kind of interesting. Here's another example which I took from the literature. It's a lithium arsenic tungstate. This was using powder data from PowGen at the SNS. I just took their data and replotted the ADPs they determined as a function of temperature to show that the displacement amplitudes and 0 point values can be related to the differences in the coordination polyhedra. There are 3 different ones here. It's 6 coordinated, and these 2 are 5 coordinated. So what I'd like to argue is that in the same way bond distances can be correlated with coordination, polyhedral size, and shape, here showing some systematics of lithium oxygen, lithium fluoride distances from the inorganic crystal structure database, ADP systematics could also provide a wealth of new insights if they were more routinely available. The last example I'm going to show is a magnetic disorder. This is done at the spallation source with the CORELLI instrument. This is another mineral analog of what appears to be a disordered magnetic system that does not show long-range order at low temperature. The iron and manganese are distributed in these octahedral sites randomly on 2 different sites. You can again find the whole solid solution. Well, I should restate that. We don't know what full range of solid solution occurs in nature, but we have several crystals with different iron manganese compositions. If you just look at the magnetic ions, they form these hexagonal, these hexagons where the M2 site's in the middle and M1's around the outside. Actually, it's the other way around, yeah. And this has all the properties for geometric frustration, and that the magnetization density at low temperature shows a antiferromagnetic transition around 32 Kelvin. This is the reciprocal space map of the diffuse scattering that we recover from the CORELLI instrument. So if you look at the fact that the magnetic scattering turns on at low temperatures, below 32 Kelvin, we can isolate the magnetic-only diffuse scattering simply by subtracting the room temperature from the low temperature, and we end up with the magnetic-only diffuse scattering. Now, if you are keen-eyed, you can see that there is some diffuse scattering even at the high temperature. And the way we are interpreting that right now is that we think there's some epitaxial intergrowths of boronite, which is a manganese silicate that occurs in these natural crystals. Nikolai Roth, who's a PhD student at the Department of Chemistry in Aarhus University, who's collaborating with us on this project, has developed the relationship between the vector magnetization density and what we're calling the 3D magnetic delta PDF. And it's simply the inverse Fourier transform of the magnetic diffuse scattering. And we take account the vector magnetization density, and I'll show you the details of the mathematics are given in these 2 papers. The paper in PRB is now is about to be in print. But the process involves first extracting the magnetic diffuse scattering, which I showed you, but I'll give you a little more detail here. We again measure the total scattering, elastically discriminated with the CORELLI instrument at both low and high temperatures, subtract the 2, and you can see the registry of the Bragg peaks is not perfect. So we end up with these, some Bragg peaks left over. So what we do is we punch and fill the Bragg peak positions with an interpolated density to smooth that out, and then we end up with something that we can work with to get the magnetic delta PDF. So here is shown the 3D magnetic delta PDF for Bixby. It allows the average spin-spin correlations to be visualized in real space coordinates. For systems with no long-range order, magnetic order, and cubic symmetry, this function is especially easy to interpret in that the negative peak indicates preference for spins to be aligned in opposite directions, shown here in blue, and then ones that are parallel are indicated in red. And you can correspond then these peaks with the separations of the neighboring or next nearest neighbor and so forth atom pairs in the structure. So we believe this is a powerful tool, a model-free way of interpreting the magnetic diffuse scattering of disordered systems, and we are doing more work on this. So you'll be hearing a lot more from Nikolai in the future on that project. Lastly, I want to show you kind of an update on the neutron diffraction at Oak Ridge, particularly for the single crystal suite of instruments. We have instruments for small unit cell, large unit cell, and as I mentioned, the CORELLI, which is particularly dedicated for diffuse scattering studies. The enabling technologies for the HIFER 4-circle, or what we call demand, the Topaz and SNAP and Mandy are all because of state-of-the-art anger cameras, detectors that are developed at Oak Ridge. Rick Rydell and his detector group lead that effort. Now, CORELLI is especially suited for diffuse scattering studies because it can elastically discriminate the total scattering. But any of the instruments that have large detector arrays are suitable for diffuse scattering studies. The HIFER HB3A instrument and the WAND instrument have been around for a long time, but both have recently been completed transformative upgrades that make them really world-class. The HIFER instrument, HB3A, is led by Huibu Chow and our newest hire, Yan Wu. And it has an upgraded detector bank here. It's now a 3x1 column of anger cameras. Each one of these is 512 by 512 pixels. And because they use solid-state silicon PMTs, they're insensitive to magnetic fields. This allows us the option to remove the chi and phi circle and put in ultra-low temperature devices or cryomagnets. And we've also been doing high-pressure work as well with diamond anvil cells. So this greatly extends the capability of this instrument to operate in either the 2-axis or the 4-axis mode. And so we've renamed the instrument Demand. As I mentioned, we've been doing high-pressure work. Here's a highlight of diamond anvil cell work led by Yan Wu that has gone up to 4.5 GPa. We've also been doing polarization experiments where we have an S-bender polarizer, also in situ pumped helium-3 polarizer or drop-in polarizer. These are going to be useful for looking at molecular magnets and magnetization density studies. Over the past 2 years, we've also upgraded the detector on the WAND instrument, which is part of the US-Japan collaborative program on neutron scattering. This instrument is switched to an EPIX-based event mode type data collection and allows for fast data collection. What's interesting here is that this instrument's led by Matthias Frunzak and another new hire, Keith Taddy, but it uses the very same Brookhaven National Laboratory 2D helium-3 detector that was removed from Benno Schoenborn's PCS detector that was decommissioned at Lance. So that detector now has a new life in this WAND-squared instrument, which is going to be a powerhouse for both single crystal and time-resolved powder studies. Topaz is the workhorse single crystal diffractometer at the SNS, despite that only 25 anger cameras out of 45 positions are available. Cell sizes up to 70 angstroms are doable. It has a conventional cryocooler, but we are also building and installing a 5 Kelvin CCR later this year. In the single crystal suite, Topaz has the most mature data collection, acquisition, and visualization tools. It's led by Xiaoping Wang and Christina Hoffman. You should know that Bob Bao, Tom Ketzel, and Art Schultz were principal external members of the Topaz instrument development team. The CORELLI instrument, as already mentioned, has this correlation chopper, which allows elastic discrimination. It's dramatically shown here with the two diffraction patterns on the right. At the top here is Benzil total scattering, and below it is the elastically discriminated pattern. You can see almost all the diffuse scattering disappears because it's all due to phonons. The CORELLI instrument is led by Feng Ye and Yaohua Liu. It has a huge repertoire of sample environments for extreme conditions, both high, low temperatures, magnetic fields, electric, high voltage, and also pressure cells, copper beryllium clamp cells, and also diamond anvil cells. We have two instruments dedicated to macromolecular crystallography, one at the HYFR, one at the SNS. Imagine has an innovative optics for beam delivery that was developed by Lee Robertson and Duku Stoika. It's led by scientists Andrei Kovalevsky and Flora Mayur. It has a wavelength filter system and a 5 Kelvin CCR, which also has been installed to expand some of the scientific portfolio into materials chemistry and physics. But currently, the program for this instrument is outstanding in macromolecular crystallography. Lastly, amongst the instrument suite is MANDI, which is currently the most powerful macromolecular neutron diffractometer in the world. It can handle very large unit cells up to 300 angstroms, and it has 40 anger cameras. Uses a gas cryocooler, but we're also exploring the possibility of a low temperature CCR. Leighton Coates is the primary instrument scientist, and he has help from Dean Miles and the Imagine scientists. We also do a lot of hands-on workshops from Oak Ridge. Here's a list of some of the ones that have happened over the past 2 years or about to happen. Noteworthy ones are the National School on Neutron and X-ray Scattering, which accommodates 60 to 70 graduate students per year and partners with Argonne and the APS. The Magnetic Structure Determination Workshop is another one that's offered biennially. The next one will be this October at Oak Ridge, and it will be a satellite meeting to the Pittsburgh Diffraction Conference, which we are also hosting in October. And another satellite meeting associated with the Pittsburgh meeting will be this one on symmetry and space group approach to modulated crystal structures. It's being organized by Xiaoping Wang. So lastly, I just want to mention that we have gotten the go-ahead from the laboratory director to start a project office for the second target station at the SNS. What this is ultimately going to be over a $1 billion project, and will greatly expand the instrument suite to having three sources: the HYFR, the first target station, the second target station. We'll be hearing much more about this in the future. 2 single crystal diffractometer concepts are maturing among the several instrument concepts that have been proposed for STS. These include Ewald one for doing macromolecular crystals and a polarized instrument for doing quantum materials. Let me acknowledge 2 important collaborations. I mentioned the US-Japan Cooperative Program on Neutron Scattering, now in its 37th year, and also the Center for Materials Crystallography at Aarhus University, led by Bo Everson. And there are actually several thousand people I should thank that have helped me to this point in my career. But I'll mention a few personally influential mentors: Rod Ewing, Jerry Gibbs, Lynn Boatner, Brian Sales, Jaime Fernandez-Baca, Feng Ye, Huibu Chao, and Claudia Ron. But these are some of the people that actually do all the work and make the Neutron single crystal diffraction program and have made it a success at Oak Ridge. And I can't get away without thanking my financial sponsor, the Department of Energy. Thank you very much.
Curious, since you're on the mountaintop now, would you comment on how you see the balance between curiosity-driven research and applied research for the vast range of territory you've described, and that obviously for the future versus the recent past?
Well, you can certainly see that in the early days, it was all curiosity-driven, right? Nowadays, we do have to have more of a balance between applied and basic research. But I think it's all important because that applied research now relies on very fundamental understanding of materials in order to optimize their properties and to make things more efficient, to make things greener. In fact, our salvation may be in finding a world where better materials can be substituted for ones that are inefficient. So.
Any other questions for Bryan? Okay, thank you. Let's give Bryan a round of applause.